Section 7.2 Regression Analysis. By definition, regression analysis is a set of statistical methods used to estimate relationships between the independent variables and a dependent variable. Look at this figure. There are the data points and blue dots, and by using the least squares technique, we find a line which represents the data points. This line is called the regression line. Here we define the terms officially in this definition. Suppose a set of experimental data points are given as in this form: x1, y1, x2, y2, and xm, ym. There are m points. So for example, at x1, the observed value of y is y1, right? And if we display these data points, then assume the graph is close to a line, as in this figure. Then we may determine a line of this form, y equals beta 0 plus beta 1x. And so that the line is as close as possible to the data points in average sense, or with least the square error. Because the line cannot pass all the data points, and we have to determine the line of this form. So we write down here, we may and must determine a line. In this case, this line is called the least squares line or the regression line. And beta 0, beta 1 are called regression coefficients. Let's see how to calculate regression line or least squares lines. Now we consider the least squares model of the form y equal beta 0 plus beta 1x for given data set. Then here for each point we have observed y value. At x1, observed y value is this one, so that for the model we have this equation. And for x2, and this is the model, and the observed y value is y2, so we have this one. So for each point we have one equation. Now for the equation, we can write it into this metric form. Here x is now the coefficients 1 and x1, because the unknown is beta 0 and beta 1. 1 is coefficient and x1 is coefficient for the first one. And for the second equation, 1 and x2 are coefficients. So the metric x is the collection of coefficients, and beta is the unknown vector, and y is the observation vector. And here, if we are using the least squares technique, then just we can use the method of normal equations. So we multiply x transpose. Then when this is invertible, then we can find the unique solution. Apparently, here this first column, and if we take here now the data in distinct points, at least two of the points, the x value are different, then this column is independent, so that X has linearly independent columns, which means that earlier in the last section, we saw a theorem saying that this metric has independent columns, then X transpose X must be invertible, right? So apparently this is independent columns, then it's invertible. Now here, practically, expressly, we can write down the metric X transpose X and the right side in this way. Okay, and that is M, the number of points, and summation of xi, and summation of xi, and summation of xi squared. There's a summation of observed values, y values, and xi, yi summation. Okay. In reality, we may construct the normal equations here pointwisely. That means that rather than making this component once, and by summation we try to construct for each data points, these are contributions, and we sum those the pointwise metric to get the final metric. And also for right side, we can get a vector, pointwise vector, and sum them to get the final right side vector. The reason we are working on this way is that now after once we get some regression line, and then once we add some more points, then we can add the contributions for additional point more easily. And or now once we try to give some weights, some points are more important than others, and then we can give some higher weight so that we can put here weight component so that we can get a better regression line. Okay. Now this idea of construction of pointwise the normal equations is useful for every other regression models. Okay. Now here, find the equation of a least squares line that best fits the given points. Okay, let's try to do some part of the computation. Now, when you work on this problem, possibly you may try to make a table x and y, like that. Okay, x is now -1 and 0, and the first components are x values, and 1 and 2. The corresponding y values are 0, 1, 2, 4, right? Okay, for x transpose x, we can get it. Here there are 4 points. So it's 4. Summation of the x values, which is now 2, and here again 2. The summation of x squared, 1, 1, 4. So it is 6, right? 1, 1, 4. Okay. How about the right side? X transpose of y. Okay, that one is, the first component is a summation of y values. This one is now 7 and xi, yi. Okay, here to here is 0 and 2 plus 8, so it is 10. So we have to solve the metric times the coefficients, the regression coefficients equals this right side. Now, by using hand, you can solve the problem. Start from the augmented metric for 2 and 2 and 6, and right side 7 and 10. You can get, if you change this portion to be the identity metric, then you can get it. For this one, it is same as 1, 3 by scaling, and 5. And now, twice subtraction will make this 0. Twice subtraction, so that 12 is subtracted minus 10. Now 20 is subtracted, so that minus 13. Right? Okay. Here, that is, okay, that is minus 10, minus 13. Okay. So we scale by using different color. Here, rather than write it again, we change this one into 0, 1, and 1.23. And 3 times subtraction, okay, from here now, 3 times subtraction will make 1, 0, and that is a 3.9, so that this is 2.1, I guess. This is 3.9, okay, 1.1. Okay, that must be 1.1, and 0, 1, 1.3. That means this is beta 0 and that is beta 1, so that the model we are seeking is here y equal beta 0 is 1.1, and the slope is 1.3 and x. So that's the final answer. Okay. Okay, now that is here. For other curves, we can use the same technique, least squares fitting method. Consider a regression model of this form is a quadratic polynomial. Then, now for given data set, we can make here the equation for each data points at x1. This model has this one, and this is observed y value. For every point, you can make an equation, and this set of equations can be written in this metric equation. Now here, beta 0, beta 1, beta 2 are forming an unknown vector, and coefficients are 1, x1, x1 squared for the first equation. So we have here, from second equation, 1, x2, x3 squared, right? So we have the collection of coefficients to become x, and that right hand side y is the observed y values. Now, if we are using the least squares technique with the normalization method, then now we can get here x transpose x. If you do practical computation, then you can reach at this one, that is beta, and x transpose y will become this one. Here we have the pattern. This is 1x x squared summation, and that is now 1x is multiplied. So xi squared, xi now cubed, and one more time xi multiplied here, so that 1 power increased. So you have this pattern. For right side, now summation of yi, xi is multiplied, and xi squared is multiplied. So you can see the pattern right? Now, for this problem, it's a self-study problem, so that try to find the least squares curve for these data points in this form. Try to do it yourself. Okay, then you'll see this result. Okay, now the regression technique or least squares technique can be used for nonlinear models. So through linearization, we can do it very effectively. Now that start from change of variables. Look at here the model. Assume we want to get here the model. We want to fit the given data points by using this model. So it is not linear because x is involved with on the bottom. In this case, we may consider a change of variables in this way. X tilde is 1 over x, and now we don't have to change y, but we try to use this change of variable. Y tilde is same as y. Then now in tilde variables, we have this one, and y tilde is same as a plus b times x tilde. So it is a linear model. By using this model, you can find a and b, and easily just the standard, by using the standard least squares formulation. Now, if we have this model, then now rather than x, we try to introduce y tilde to be 1 over y. Then it can be written in this form. Again, this is a linear model, so that you can get the least squares solution quite easily by using the standard technique. Now this is exponential function. For this model, we have to decide C and D, the coefficients. Now in order to do that, we keep x variable, but for y variable, we take logarithm. Then here, if we are taking logarithm, then there is a logarithm of y is the same as, now logarithm of these terms, that is same as logarithm of this plus logarithm of c. So that we can see that dx plus logarithm of c, right? So once we apply logarithm from both sides, then here, along with the logarithm y tilde, we can write in this way. That is exactly from here. Y tilde is same as logarithm c plus d x tilde. Now this is a linear model, and we'll get the output will be logarithm c. Out of the logarithm c, we can get c by taking exponential function, right? Now here, consider this model. Then we introduce 1 over y to be y tilde. Then it becomes now numerator. And for logarithm x, now we introduce x tilde. Then it will become again a linear model. This table shows just a few examples of linearization. For other nonlinear models, you can use your imagination and creativity to get linearized model or some very approximated linear model. The reason we need linearization is that sometimes we have to solve the nonlinear regression model by using, for example, Newton's method. in this case, you have to give it really good initialization for the parameters by using linearization or approximate the model. You can get good approximated parameters. Then from that moment, you can get the much better estimation by using the Newton method. Okay, here, these are data points. And find the best fitting curve of the form. This is exponential function for the data. So if we make a scatter plot, then it is given in this way. Looks like an exponential curve, or it can be a quadratic curve. But anyway, in this example, we decide to find the best fitting curve of this form. Now, okay, after taking logarithm, and here we have that. So we are introducing the change variable. For logarithm y, we are using capital Y, and for small x, little x, we are using capital X rather than tilde notation. We are using capital variables. And here for logarithm C, we are using A0, and for D, A1. Then the model, we can decide is this one. This is line. So we apply the linear least squares method to get A0 and A1. After getting these values, and we can recover and C and D. A1 is D is directly from A1. Now C can be found from here. Now C is exponential of A0, right? Okay. This is a small code in Maple. Now here, okay, in fact, data is made, okay, data is given from here. Okay, that data is not shown, but anyway, from there on, and y is logarithm of y. So we are taking for y values logarithm, so that here x ln y, and this x value is the same as the original x values, and now y values, in fact, that's capital Y, which is logarithm of small y values. Okay, so this change of variable means that in programming, you have to apply the same operation for data values, so that in this data set, the y value cannot have negative or 0. And once it is appearing, then also you decide to find this model. Then here the value, the other values are positive, y values are positive, then somewhere and some data point having negative y value, you have to discard those the data points. If you try to use that, then the algorithm will break. Okay. So we take a logarithm, and for those transformed data, we try to find the curve in the form of now a plus bx. Then we have that. So that is now a0, that is a1, and d is decided from this one directly. Now c is the exponential of this one, so that we can have that. So here the desired model is this one, c times exponential of dx. Okay, that is one. Now we here to make a plot for the curve we found. So these are theta points, and this is the model we found by using the linearized least squared method. It's fitting well, right? Okay, that's the end of the section. Thank you.